Hello, and welcome to Piecewise Defined Functions. My name's Tuesday Johnson. Here's an introduction to a concept with applications. All right, so let's look at some common graphs. And there's 8 common graphs that you really need to know. We might not use all of them this semester, but these are kind of the 8 basic algebraic functions. A linear function has the graph that's a line, right? So it's just a straight line. Anytime a mathematician says a line, they mean a straight line. We would call this a curve. Anything that has a bend to it would be a curve. So these are all curves. Even this one is made up of straight lines. I know, it's weird. A squared, all right, so let me write in the equations. It might be like y equals x. A squared equation would be y equals x squared. This is what its basic graph looks like. Y equals x cubed. It's called a cubed graph because it's a third power squared. A square root graph, square root of x, right, is only a piece of it. And you can see the domains and the ranges of these various functions as well. Absolute value of x, right, always makes the result non-negative. A rational function, y equals 1 over x. Notice there's some issues here at 0. Things are getting weird. An exponential function, and we'll get to these shortly. I'm going to call it y equals b to the x. The main difference between an exponential function and, say, a polynomial function is the location of the x. Here there's specific numbers in the exponents. Here there will be a specific number in the base. That's why we use b for base. And the exponent has the variable. And logarithmic, we will also get to later, so don't worry about this yet. But our graphs, notice these two are very similar. All right, so we're going to use these 8 graphs, probably more. We can use pieces of them to create new functions called piecewise defined functions. Piecewise defined, why? Because we define it in pieces. Mathematicians, super creative. Okay, so here's a piecewise defined function. Now, I'm just going to pop up this graph that I made with it. I made this graph with Desmos, DESMOS.com. Desmos.com for all your graphing needs. No, they don't pay me, but I love it, and it's free. And it's free for Android and Apple users. So this function says, for an input of x, if x is less than -2, then we just get out whatever we put in. So we see here at -2, I'm going to put a circle. I'm going to put an open circle. That open circle says I can't equal -2, but I could get super close to it. I think of it like a tent stake, right? If you're putting up your tent, my tent looks like a house, I guess. Let's put a zipper in here so it looks a little more tent-like. There we go. Now our tent is open. You have to stake your tent down. My daughter ended up in the lake one day because they didn't stake the tent down. All right, these are tent stakes. This little open circle here, that's just a placeholder. It's saying, hey, if I could get here, I would, but I can't get quite all the way. All right, so that's what that open circle means. It's like a tent stake. This x squared minus 4 between -2. Okay, so we have an equal. All right, so x is literally between -2 and 1. So this is our position here. See that equal to? That equal to is going to have us put in a solid dot. That's actually tent space. We could sleep in there. All right, that's solid. We can use it. Staking, right? We're staking out our territory, but we're not going to use it. Here, we're sleeping in the tent. Can x equal 1? No, it cannot. So we'll put an open, maybe. We'll put an open circle on it. All right. Well, this one's better, but it does the job. Absolute value of x minus 5. If x is greater than or equal to 1, because it's greater than or equal, I'm going to put a solid dot. Now, the only time you will have dots or open circles is at these cut values. Okay, only at these numbers will you have open or closed dots. The rest of the time, it's just a point on the graph. It's all good. It's all the same. But we only graph on certain sections based on our domain for the given range element. Actually, this is the given rule, not range. All right. So here we have our graph, and I'm just going to quickly make it match the one we just did. There we go. Let's look at how to use this graph to evaluate. So f of 0. Now, if I look in here, I see that 0 is in between -2 and 1, so I'm probably going to use this 0 squared minus 4. So f of 0, 0 is between -2 and 1. So I would use f of 0 is something squared minus 4. I'm still using my skeleton. And we can see that on the graph as well. Here at 0, I go 1, 2, 3, -4. So for me, the graph would be easier, but algebraically, it's important to put ourselves in the correct domain region. So f of 2, where's 2? Well, that's -2. It stops at 1. That's bigger than 1. So 2 is greater than or equal to 1. So I'll use my skeleton of absolute value of something minus 5. Here it's a 2. I know that 2 minus 5 is -3. Absolute values do not turn subtraction into addition. You do the problem, and then at the end, you make it non-negative. Let's check again. 1, 2 at 2. Here we are at 3. Let me square in these answers so that they're easy to find with the work shown. F of -2. Let's look at the graph first. At -2, it looks like I have two options, but we put in the solid dot and the open circle for a reason. It tells us we are here, but we cannot use this one. So it turns out that -2 is 0. And if we put it in here, right, -2, -2 squared, and that's where the, let me write this down real quick. -2 is equal to -2, so it's less than or equal to, which is less than 1. So we would use the area, the skeleton of something squared, minus 4. What's being squared? It's the -2. And that's where the skeleton comes in handy, is reminding you to square that negative with the 2. That's what I really like about it. So -2 squared is 4. 4 minus 4 is 0, and we have the same answer. Graphically or algebraically, you can find these answers. Let's look at some examples, some applications. So my brother-in-law works for El Paso Electric, and I have no idea how much money he makes because that's the way it should be. I don't care. But I looked it up on the website, and a certain lineman working for El Paso Electric Company earns about $44 an hour for a 40-hour work week. If they make time and a half for overtime, you know, power goes out in the middle of the night, they get called up, they're making good money. The money they deserve. Write the corresponding piecewise defined function. Okay. $44 per hour for a 40-hour work week. So let's let X be the number of hours worked. Okay, so if X is the number of hours worked, from 0 to 40 hours, right, a 40-hour work week, from 0 to 40 hours, we're going to multiply 44 times X, the number of hours worked. No big deal. But if we go more than 40 hours, this is overtime, right? Time and a half means we make $44 regular, and then we make half of that extra. I almost wrote a 2 there. Yes, that's exactly what it was. So that's how we get our $66 per hour over 40. But what's the 1760 all about? 1760, well, let's see. If we work 40 hours at $44 per hour, wow, I got lost in the middle of that one, didn't I? 4 times zeros. 4 times 4 is 16. 16 and 1 is 17. Oh my. This is what they would make in 1 week if they only worked their 40 hours. So this takes into account the regular pay for the week plus the overtime. All right, so you kind of look at how it goes in various ways. Let's look at another example of piecewise defined functions. United States tax rates. This particular image is only for single filers. It's definite for married filing jointly, head of household. So many different brackets. I don't even remember the rest of them. We're only going to look at single taxpayers. All right, so how much would a single taxpayer, how much tax would a single person earning a taxable income of $10,275 owe at the end of this year, whatever tax year this happens to be? So it's not written in function form, right? Only in math class will it be f of x equals. In real life, it's just the function. So taxable income bracket. So these are our little domain values. This is where we're going to find what we do. And then this is going to be our rule. Okay, so 10,000. Oh, look at that. It's exactly this amount. So the rule is 10% of taxable income. So I'll take 10% of 10,275. I can write. All right, I erased all the ink on the slide. That's cool. 10% of 10,275. 10% would be $1,027.50. Notice, all right, so if you make 10,275, you're going to have to pay 10% of your taxable income in order to pay for whatever services. Notice this 1,027. Did I say 10,000? If you make 10,000, you pay 1,000. This 1,027.50 is the base that you add more on if you have a higher taxable income. Just like the lineman, we take the previous tax owed and then the extra because you made extra money. Let's look at another example. How much tax would a single person earning a taxable income of $65,391 owe at the end of this year? All right, so we're looking at $65,000. We're going to be in this range, right? 65 is between 41 and 89. So my tax is $4,807.50 plus 22% of the amount over 41,700. Okay, so of 65,391 minus 41,775. Right? 4,807.50. Okay, plus, literally plus 22% in percentage. 22% is 0.22. The amount over. So I'll take how much I made and I'll subtract that. That's our amount over. We have 4807.50 plus 22% of 23,613. That's not true. 616. All right. Do the subtraction first, order of operations. Now I'll multiply and add, and we'll end up with $10,003.02. So if you end up with a taxable income of $65,391, you'll owe a single filer will owe tax of $10,003.02. That's it. Piecewise defined functions. Thank you for watching. Have a great day.